All right, let's dive right into this explainer. When you picture a perfectly clear night sky, completely filled with stars, it looks so peaceful, right? But every single one of those bright little dots you see up there is actually a giant nuclear power plant, just churning out almost incomprehensible amounts of energy every single second. But here is the crazy secret of the cosmos. Stars don't live forever. Just like anything alive here on Earth, they're born, they change, and eventually they die. And while some stars just kind of quietly fade to black, the absolute most massive stars in the universe, they go out with one of the most spectacular, violent explosions ever witnessed. We call these absolute monster explosions supernovas.
So, that brings us to the ultimate cosmic mystery, right? Why do stars explode in the first place? What could possibly cause such a massive blast out in the vacuum of space? Teachers, this is actually a perfect moment to pause the explainer. Have your class work together and toss around some hypotheses. What do you think happens inside a star to make it blow up like that? Take a second, and whenever you're ready to investigate, just hit play.
Okay, here is our shared cosmic roadmap for today. We'll be hitting Part 1, How a Star is Born. Part 2, Gravity versus Nuclear Fusion. Part 3, The Supernova Explosion. Part 4, What Remains Behind. And finally, Part 5, We Are All Stardust.
Let's kick things off with Part 1, How a Star is Born. To really wrap our heads around the explosive death of a massive star, we have to rewind and look at its quiet beginnings. Before a star is even a star, it's a nebula. Basically, it's just this giant, sprawling cloud of gas and cosmic dust floating out in space. Over millions of years, gravity acts like this incredibly slow, patient vacuum cleaner, pulling all that loose material together. As more and more dust gathers, the center gets unbelievably dense and unimaginably hot. A star is truly sparked into existence from these clouds only when the temperature inside hits roughly 15 million degrees Celsius. Let that sink in. 15 million degrees.
Once that core hits 15 million degrees, the star's engine fires up. We call this nuclear fusion. It's the process where hydrogen atoms literally smash into each other and fuse to form helium, and doing that releases mind-boggling amounts of energy. That energy creates this massive outward push, which fights right back against the crushing inward pull of the star's own gravity. As long as those two forces are perfectly balanced, the star stays stable and shines brightly for billions of years.
Moving on to Part 2, Gravity versus Nuclear Fusion.
Because nothing lasts forever, right? Eventually, the star's hydrogen fuel starts running low, setting up what is literally the most epic arm wrestling match in the universe. On one side, you have gravity pulling inward, trying its hardest to crush the star. On the other side, nuclear fusion is pushing outward with the force of billions of nuclear bombs. But as the hydrogen gets scarce, that fusion engine starts to sputter. The outward push gets a lot weaker. But gravity? Gravity never gets tired. It never stops pulling. Without that outward energy, gravity starts aggressively crushing the core.
Now, a massive star doesn't just give up when the hydrogen is gone. As gravity crushes the core, it gets even hotter, and the star frantically starts fusing heavier and heavier elements just to keep that outward pressure alive. Helium turns to carbon, carbon into oxygen. Then you get neon, magnesium, silicon. It's like a cosmic factory running on complete overdrive. But then it hits step 4, iron. Iron is the fatal flaw. Fusing lighter elements makes energy, but fusing iron, it actually consumes energy. It's a complete dead end for the star.
Which brings us right to Part 3, the supernova explosion.
The moment that core becomes mostly iron, the star entirely loses its ability to hold itself up. Gravity violently, instantly wins the battle. Notice the crazy shift in speed here. After billions of years of just slowly burning, the actual collapse happens in a flash. In less than 1 second, gravity crushes the core inward. In fractions of a second, all that outer material comes crashing down, hits the ultra-dense iron center, and bounces back. Seconds later, that rebound creates this gargantuan shockwave racing outward, completely obliterating the star. That violent blast is the supernova.
Okay, try to imagine this scale with your class for a second. For a brief window, just one single exploding star can outshine an entire galaxy made of hundreds of billions of stars. It's absolutely wild. This single blast is hurling massive amounts of gas and newly forged elements across deep space at literally millions of kilometers per hour.
Now for Part 4, What Remains Behind.
The explosion doesn't just wipe the slate clean, it leaves behind some of the weirdest, most extreme objects in physics. Class, think about this. If the original star was big enough, the crushed core it leaves behind becomes a neutron star.
It packs more mass than our entire sun into a tiny sphere only about 20 kilometers across. It's so dense that just one single teaspoon of neutron star material would weigh billions of tons here on Earth. 1 teaspoon!
But there's an even more extreme scenario. If the original star was an absolute titan, gravity just keeps crushing that leftover core until a black hole forms. The gravity of a black hole is so intensely powerful that absolutely nothing, not even light itself, can escape it. These ghostly remnants, whether they're ultra-dense spheres or light-trapping voids, they just sit there, shaping the universe long after the star itself is gone.
And finally, Part 5. We are all stardust.
This is where it all comes together. Because the real climax of this story isn't some explosion millions of light years away. It's the connection sitting right there at your desks. Seriously, look around your classroom right now. The calcium making up your bones, the oxygen you're breathing, the iron in your blood, the carbon in every single cell of your body. Nearly all of those heavy elements were forged inside the intense, frantic heat of ancient stars. When those stars exploded, they scattered those crucial elements across the universe, eventually coming together to form Earth and, well, you.
There's a great quote that says, "In the universe, every ending is also the beginning of something new. Every human being is quite literally made of stardust." The violent death of a massive star wasn't just some random fireworks show. It was the absolutely essential first step to creating life. The atoms in your left hand might have come from a completely different supernova than the atoms in your right hand, but they all came from the stars.
So, the next time you look up at the night sky, just remember, you're actually looking at your origins, which leaves us with one final, kind of mind-blowing question. Since you are made of ancient stars, what will the atoms inside of you become billions of years from now? I hope this sparks a fantastic post-explainer discussion in your classroom today. Never stop looking up, and definitely never stop asking questions. Thanks so much for joining me on this explainer, and have an awesome discussion.